Okay, last meeting, we had this part in here written. This is step 6 of the steps that was outlined in the slide that was shared to you. And this step is concerned with determining the boiling point rise of your solutions in each of our effects. In our problem, we have 3 effects, so we have to determine 3 BPRs. That for effect 1, 2, and 3. Now, when you speak of BPR, that would be the difference between the elevated boiling point of your solution. Elevated in the sense because there were solids already present on it, and the saturation temperature. So these T1, T2, and T3 are saturation temperatures. Now, I'd like to share to you the exact step or discussion that John Kuplis have discussed in his book. That way, we will have a basis on the particular modification that I did for this particular step. So I will share that PDF copy, the PDF copy of John Kuplis. Okay. I hope you can see the PDF copy of John Kuplis in here. He has labeled the topic, the step-by-step calculation for triple effect evaporators. This same step-by-step calculation could be used to other multiple effect system. Now, I'd like to go to that part which we're not able to perform for the problem that we lost discussed because there was no BPR in that. In here, there is going to be a BPR because the percentage of the solids present in the solution is already 10% to 50%. So we cannot anymore neglect any elevation in the boiling point temperatures. Now in step 3, it says here that using equation 8.5-6, this is equation 8.5-6, which was shared to you as well on determining the delta T's for each effect. Estimate the temperature drops in your effects. Any effect that has an extra heating load, such as cold feed, requires a proportionately larger delta T. Now, in the case of a cold feed, oftentimes class, as I have observed, they are being preheated before they are fed to the first effect or the effect that will process it. Now, then calculate the boiling point in each effect. So we have done this already. Now, there is an added paragraph here that discusses about how will you deal with a case wherein you have the BPR already. So if a boiling point rise is present, estimate the pressure. So I'd like to emphasize on the term that was used here by the author. It says here you are to estimate the pressure in effects 1 and 2, because in the case of a triple effect evaporation system, then your last effect pressure should be given, because it's always step 1 that you determine the boiling point of the last effect. So then it says here that you are to estimate the pressure in effects 1 and 2 and determine the BPR in each of the 3 effects. Now, how will this let you determine the BPR in the first place? After you have done estimating the pressure in each of your effects, you are to determine the saturation temperature now with all your effects. So you have already determined the third effect. So it follows that with the pressure, you can go to your steam tables and determine the saturation temperature for each of those estimated pressure. Then that would be your basis for the saturation temperature for effects 1 and 2. If you already have the saturation temperatures of effects 1 and 2, that would lead you, upon using the During's chart, which we will go back again later, to the boiling point of your solution. Because During's chart does not give you the BPR. What does it give you is the boiling point already. That is the elevated boiling point of your solution based on the solids that it contains and based on its saturation temperature. So that's the main reason here that the author emphasize that you are to estimate the pressure. In our case, when you estimate, then everybody will have a different estimate for that sense, right? Because you only have the pressure of the last effect and you are free to estimate the pressures, that is the operating pressures of effects 1 and 2. That would be very tedious for the one who's going to go through your solution because each of you will have your own estimate for that sense. Now, I'd like to read us further on the next statement, which says that only a crude pressure estimate is needed since BPR is almost independent of pressure. So the author is saying that your estimate will be something that is crude because anyway, the BPR is independent of pressure. So the purpose that you're just making a crude estimate, it's because you need the saturation temperature in the Durings chart. You need both the solid content and the saturation temperature in the Durings chart. So without that saturation temperature, that will be needing the pressure in each effect. You cannot determine the boiling point of your solution, which will yield to the BPR. Then it says here further that then the summation of delta T available for heat transfer without the superheat is obtained by subtracting the sum of all 3 BPRs from the overall delta T. So meaning, if our summation of delta T then with negligible boiling point is simply the difference in the steam temperature and the saturation temperature of the last effect, now if you have already the BPRs, you are to take the sum of all 3 and then subtract it further to the difference of these 2. Only then can you estimate the true summation as delta T sub 1, delta T sub 2, and delta T sub 3. Based on, so where you're going to base the delta T1, delta T2, and delta T3, you're going to base it on the, of course, the formula that was also shared to you. Now, the thing class with this, with you estimating the pressure in the first place, if I'm going to ask, how will you estimate the pressure in the first 2 effects, knowing that your third effect has a pressure of, let me check, what's the pressure of the third effect? The pressure of your third effect is 10.34. Okay, it's 10.34. And you are asked to estimate the pressure of the first 2. That way you can get the saturation temperature from the steam tables. Now, if you're going to estimate, if I'm going to ask you, what will be the basis of your estimates for the pressure? How will then the pressure here behave, if I'm going to ask you, for your triple effect evaporation system? For example, this is 10.34. What should be your P sub 2? And what should be your P sub 1? Anybody who can guess how will the trending be in the pressure in this case? No idea. How will you estimate the pressures in the second and in the first effect? So somebody wrote increasing. Very good, Drexel. So when you speak of increasing, Drexel is saying that if it's increasing, if my interpretation of your answer is right, it would be increasing in the sense from third effect, it should be increasing down to the first effect. When you have a multiple effect evaporation system, we expect the boiling points of your solution starting from the first effect down to decrease. This same behavior is to be exhibited by the operating pressures in each of the effect. So if you have this as 10.34, somebody may place this at 25, and somebody may place this at 35. So it has to be increasing from the third effect down to the first effect. So somebody wrote, okay, so you wrote your attendance. No need, class, because I'm going to take your screenshot later. Okay, so this is it. You have the estimate increasing from the third effect down to the first effect. But the Excel was, in my case, I will have it 25, 35. The Excel may have it probably 30, 40. or 20. So all of you will have different pressures and all of you will have different temperatures. So my suggestion then to my students before, since it was anyway stated, I'll go back to the PDF copy of the book, huh? Where was that? Here. Since anyway it was stated that your BPR, the BPR is independent of the pressure, which in the first place you estimated, then we will just determine the delta T first without the BPR. Just like the way we do it with negligible boiling point delta T's, wherein we only had the steam temperature and the temperature of the last effect subtracted, then we solve for the delta T's without the BPR. Then we will have a saturation temperature now for the two effects in which we don't have. And then we use that saturation temperature in the During's chart. That way, we can get the boiling point of your solution. With the boiling point of your solution now taken from the During's chart, you can get the BPR of each of the effects. So with the BPRs of each of your effect, you can go back now to correcting. So I use the term to correcting the original summation of delta T that we computed based on this difference only of two temperatures to the delta T effective where you already accounted for the 3 BPRs. And then that would make the one who's going to go through your work easy to correct it or check your work, because you will all have the same starting point, rather than each of you having to estimate the pressure in each of the effects and then have your own BPs, have your own BPRs. It's just like checking an individual solutions. All of your solution will be unique from each other. So that would be very difficult. So I'm suggesting to my student that first determine the delta T's without BPR, then delta T effective with the BPRs later. Okay, I'm using this phrase here that anyhow the BPR is independent of the pressure that you have estimated. So we will do that where we ended yesterday in our solution. So in here, I have placed in here the BPRs of the three, and I need this. I'll use a different. I need the BP of solution 1, I need the BP of solution 2, and I need the boiling point of solution T. So associated with this step 6, that way you will not have different pressures to estimate. Go to the next page. We'll just first determine the summation of delta T only. We'll differentiate it with the new delta T or the corrected delta T with the BPRs later as the delta T effective. So in this case, we will just determine the temperature difference, or rather the difference of the temperature of the steam and that of the last effect. Okay, so we have already the temperature of the last effect, but I think we're not able to get the saturation temperature for hours. Oh, it's given already. So this time our problem gives us the temperature of our steam. So we can use it here. So good, we will not have to go back to the steam tables and find for the steam temperature. So 178.1, and then we have T3. 46.36. So you will have a crude delta T here of 131.74. So kindly get your calculator, so we'll have, you can check as well my values here. So we can make a temperature distribution diagram here. This time we'll have divisions in these 3 divisions. Now I will have summation of delta T1 summation of delta T2, or rather delta T2 only, and delta T3. This will be our steam temperature, which is 178.1, and this will be our last effect boiling point, T3, which is 46.36. Based on equation 8.5-6, same equation that we used with no BPR, we can determine the delta 1, the delta 2, and the delta 3. So with your delta T sub 1, you will have the summation of your delta T times 1 over U1. Your denominator will be 1 over U1 plus 1 over U2 plus 1 over U3. In this case, our U's are equal. So I will just place here one particular delta T formula. I leave the rest to you. So in here, you will have 131.74, and you will need to divide this by the U that is uniform for our system. In this case, it's 2,840. So you have here 2,840. And you will have here 1 over 2,840. We'll just multiply this by 3. Because anyway, they will be just the same. So you'll be getting a delta T1, which is, so you will have a value here for delta T1. You use the same formula for delta T2 and delta T3 here, changing the 1 over U1 to 1 over U2 for delta T2 and 1 over U3 for delta T3. Okay, I'll place here delta T2 and delta T3. Okay, so can we have that here? 3 divided by 2,840. So this is 43.91. So please check my value. So for the other one, you will still have for the other delta T's, since we have the same, by the way, overall heat transfer coefficient, they will be just the same as this, right? So there's no need for you to compute because they have the same use anyhow. So we have 43.91. This is also 43.91. Okay. So if we go back to our temperature distribution diagram, you just increment the temperatures here. So I will place here T sub 1, T sub 2, and we have T sub 3. So from 178.1, we subtract the 43.91. That would be 134 here. 0.19, and we subtract another 43.91, that would be 90.28, and we subtract another 43.91, that should give us 46.37, more or less the same as our last here. Okay, so this would be now, I'll just use a different font. So this will be now the saturation temperature that you will use in the Durings chart to get the BP of your solution that will be substituted here to get the individual BPRs. So if we'll have, if you'll use this temperature now, I'll just place it in here from steam, oh no, not steam table. Okay, from Doreen's chart. Okay, so you will have delta T1, which is T1 only. Your T1 here is 134.19. And you use here together with this one, the solid content. $50. So we'll have here XL1 50%. Okay, somebody wrote on the chat box. Okay. And then we'll have T2. To get it, our temperature distribution diagram, 90.28. Your XL2 here, we computed based on our first assumption. So XL2 0.22. And we have T3 46.36. And you'll have the XL3 originally given in the problem to be 0.136. By the way, it's not given. We determined it just like XL2. I keep on thinking of the feed solid content as solid content as XL3, so 0.136. Okay, so this will be the pair of information that you will be needing when you use your Doreen's chart to get the BP of your solution, the BP here that we'd like to place in here. Okay, so I'll go to a copy of Janku, please, a soft copy of Janku, please, so we can get the BP of our solution. Can you please take a screenshot of the values that we have in here so I can ask you later and we can get the value of the BP of the solution from the Doreen's chart. So 1, 2, 3, 4, 5. So I hope you have taken already a screenshot so we will not have to go back again to this page. Okay, I'll share the copy of Janku, please, where we have the Doreen's chart. Okay, here it is. Excuse me, class. Excuse me. So we'll just... Okay, McCabe has also one. So in here, you have the boiling point of water. The boiling point of water is the saturation temperature that we got out of the estimate of the delta T's. Then we have the solid content here, the line here, and we will read the boiling point of the solution either on the left side or on the right side, depending on our desired unit, depending also on the given unit. So our temperatures are given in Celsius. So then we'll be using this particular part here. Then we'll go down and then read on the left the corresponding boiling point of our solution. Somebody wrote in the chat. Okay. Can you tell me, please, what is our saturation temperature for effect number 1? Because it's like 50% NaOH. So what's our saturation temperature for that? Can you place it on the chat box? Okay. I ask you to... Anyway, I'll go back to our... So 134.19 is the saturation temperature. That's the boiling point of water, pure water, if it does not have any solid content on it. So we'll use the 134.19 degrees Celsius and the 50% solid. So where is it? So we'll have 134. So this is 0, 25, 50, 75, 100, 125. By the way, what is the temperature? 134.19. So malapaw siya. Let me check us, ha? If you're using if you're using during start, it's only until 130 in here. This is 130. And if you're going to estimate, you will have another same length as this in here. That's 135. Okay. You may approximate. As for the 50% NaOH, this is the 50% NaOH line. So if you go up and project it here, it will be something like this. It will extend there. I hope you're with me. We'll change the font to black. Okay, because so I'll project the 50%, or in this case, you can use your handbook. Okay, you may use your handbook in this case, since this one you just roughly estimate. This is 135, and your 134 probably, since these are in 5, so you have 1, 2, 3, 4, so somewhere 134.1 somewhere here. Okay, it's a different one. You just project it upwards to this projected line for the 50% solution. So I'll go up. This is my 134.1. Okay, the let me check, 134.19 to be exact. So your 134.19 is this point here. Sorry. And I'll go up. I hope you can still see the chart. You go up until you reach this line, the projected 50% solids line, NaOH. So this is that point. However, this point is also way up here. So you have here 125. The extension probably is in here 130. For the temperature, I'm referring to the boiling point of your solution, the elevated boiling point. If you will have here 125, this is 130. This is, I'm just estimating the length, so 135. And here, somewhere here is 140. So more or less, the boiling point of your solution is in here. This will be your BP1 based on our estimate. 125, 130, 135, 140, and it's somewhere in here based on my projection. Okay, so more or less, it's 137.5. It's just anyway an estimate. So your BPR, I'll close, Can't find my board. Okay. So I can place here my BPR to be 137.5. Now the T sub 1 is the T sub 1 that we have in here, 134.19. Now the difference of these two will lead you to the BPR. For the BP of the solution in the second effect, you use the same process. Okay, so in our second effect, the temperature saturation this time is lower. It's 90.28, and your solid content is 0.22. So if you'll just approximate it to 90 and 0.22, you go back to our Doreen chart, 90 So your 90, 75, 80, 85, 90. This is your 90. Wait, 75, 100. So this is the not the calibration here. 80, 85, 90, 95. Okay, so if it's 90, somewhere here, okay, this is our temperature, 90.28. We look for the 22% solid line. We don't have that, but we have instead the 20 and the 30. So we can approximate where the 22 is. It's farthest from the 30, but nearest to the 20% line. So I'd like to go down and then more or less rest here. Where is it? 20. This is your 20. 22 will be a little bit here. So I'll go a little left. So more or less, class, this is the point. The 90.28 and the 22% solid, this one is already 30. So 22 is a little bit below. So this one. And then read here the BP. BP2, this is already BP of your solution 2. So if this is 100 and this is 105, so it's a little bit around 103. Anyway, you're estimating everything, so 103. Have here 103 minus your T sub 2, 90.28. Okay, the last will be the BP of your solution 3. So we'll base it on, of course, the T sub 3, which is 46.36 and this percent solids. So we'll just round this off to 0.14. This one is 46. So we go back again to our ring chart, 46 and 14. Okay. So 46, this is 45, 46, a little after this, and 0.14. This is 10 here. Wow, very small. This is your 10. The second to the last line is 10. So your 14 will be, so I'll go down 46 until I reach this second to the last line. Second to the last line. So it's 13. So a little bit above this one. Oh my. So ang may 2020 vision that this will be your time to shine. 10, 2015. So I will go to the left for the 45. This one a little bit to the right. Okay, approximate na ni kay Miss Alex. This is very crude. Okay, this is around somewhere here. We'll approximate it to a little bit about above 10, 46. I go left. So mga 50. Sige. I'll just write it as 50. Okay, this is the boiling point of your solution. BP3. Okay. So your reading will really be varying because not everyone may have the same reading. So 50. I'll go back to where we have, where we are on our solution. So this is 50. So 50 minus 46.36, right? 46.36. You have it here. Now you have the 3 BPRs. So can you get the 3 BPRs? So we have 137.19 minus 134.19. Oh, this is 5, not 19. So you have a 3.31 here. Oh, it's not there. So 103 minus 90.28, 12.72, and 50 minus 46.36. You have 3.64. Now we will get then the summation of BPRs. So we'll get the sum of the three. That should give you 19.67. With this, you can now determine your delta T effective. So your summation of delta T effective is your TS, temperature of the steam, minus the boiling point of the last effect, minus the summation of BPRs. So in our case, we only had 3. So our steam is 178.1. This is 46.36. And we have here 19.67. So we have a delta T effective of 112.07. With this new delta T effective class, you will determine your delta T sub 1, your true delta T sub 1, and delta T sub 2, and delta T sub 3, which will all be actually equal because of the because of the same summation of delta U's. So you will have now, this is being equal to the summation of delta T effective. Okay, summation of delta T effective times 1 over U, depending kung ano na siya nga U. In this case, they're all the same. So in this case, it's either 1, 2, or 3. And you have here 3 times 1 over U because they have the same U anyhow. So what is the value of our summation of delta T1? We label this as prime because these are, by the way, already corrected based on the delta T effective. Okay, so Pelasha. Can you solve for it? So you have 112.07. We divide it by, what's the delta U? Rather, what's the U? 2840. 2840. Divide by 2840 divided by 3 times 2840. Please check my value. Is this 37.36? Oh, correct. So 37.36 will be our new summation, or rather, I keep on saying summation, and your new delta T's. This would be your new saturation temperatures. And this will be the temperatures that you will use in finding the saturated vapor enthalpy from the table. But that particular saturated vapor enthalpy will have a corresponding increase. We call it the superheat because we have the BPR. And the BPR that you will be using are the BPRs that we have in here. Okay, so I'll just give you as an example. We have already 37.36. So this will be our corrected temperature distribution diagram now. Oh. Okay, anybody who has any idea how you're going to now construct your new temperature distribution diagram? Anybody? There, you have here now your TS. So you have your saturation temperature for effect 1, saturation temperature for effect 2, and saturation temperature for effect 3. This is 17. Why did I write T3? TS. TS. So this is 178.1. We have this as 46.36. I forgot the other two. Well, right, ha? 90.28 and 134.19. So 134.19 and 90.28. Let me see. Oh, 134.19, 90.28. What do you think will be the new construction here? What do I have here? I will give you an idea. I'll place here this one. How will your temperature distribution diagram now work? Anybody who has an idea or anyone who already scanned your John Cookleys or McCabe on this? What do you have in here? Remember, this is already your delta T1 prime, delta 2 prime, and delta 3 prime. Place here BPR 1, BPR 2, and BPR 3. Okay, somebody wrote on the chat box. BPR1. BPR1B, BPR2, and BPR3. It takes patience to solve multiple effect evaporation problem. I know you are already, my goodness, what is it that we're doing here? In the industry, they have already softwares that does this for them. But it's important as engineers that you know how the software came about. So while you have this one here is delta T1 prime, delta T2 prime, delta T3 prime. Your delta T1 prime at least is 37.36, the same with the rest. Okay, ano yung purpose yun eh? Okay, this will give you the boiling point of your solution in effect 1 here. This will give you the boiling point of the solution in effect 2, and this will give you the boiling point of the solution in effect 3. If we'll do our manner of subtraction, 178.1 minus 37.36. That should give you 140.74. Your BPR1, somebody wrote, right? Your BPR1, where is our BPR1? This, okay, wait okay, on the chat box. You have 3.31. This is 3.31. Okay, then is this your true temperature already? 134.9. If you go down from 178.1 using this delta T1 prime, you have 37.36 as your delta T effective. So that will give you the BP of your solution to be 140.74. Is this right, class? 178.1 and 37.36, 140. Your BPR in effect 1, did I get it right? So 3.31. So if it's 3.31, the T1 that you're going to use later on when you find the saturation or the saturated vapor enthalpy will be the difference of 170 point, or rather 140.74 and this 3.31, which will be, I'll place it here, minus 3.31. So it will give you 137. 137.43. Now, if we lower down this 137.43 by another 37.36, that will give you 100 here, 100.07. Our BPR2, the boiling point rise in effect 2, is 12.72. So we will decrease this one by 12.72 because that's your BPR2. I'll place it here so you will have a basis. So 12.72. Your new saturation temperature that you will use when you read your saturated vapor enthalpy together with liquid is 100 minus 12. So this would be 87. 87.35. Subtracting again another 37.36, you will have 49.99. And we subtract BP3, which is BPR3, which is 3.64. This is 3.64. So your 49.99 here minus 3.64, you will have 46.35. So you will know whether you're doing the right thing if you will really more or less end up with the same value that you have here at the bottom. This value, they should agree. The value of these two. The ones that I placed in parentheses will be now the temperatures that you will use in the steam table to get your saturated vapor and liquid enthalpies. Okay, this one for the energy balance that you will be using. Okay, and then what about the superheat? So I mentioned a while ago that there should be a superheat in this case because we have already BPR. I'll just give you as an example because anyway, you know already how to do your energy balance, your material balance, and all the steps that you need to do after this particular 3 steps. This is what you're going to do. Example from steam tables at T saturation, let's say I'll use not S because that's for steam. I'll use T1 137.43. You will have to get the saturated vapor enthalpy example, and you will get the saturated liquid enthalpy. Can you please read these values from your table? You have your steam tables there. If there's a need for you to interpolate, interpolate, and I will show you how to reflect the correct saturated vapor, the correct enthalpy of the vapor when you do already energy balance using this one. Because this has to be corrected. When you get the saturated vapor enthalpy based on this temperature in your steam tables, when you use it in your energy balance later on, you have to add to this the superheat. It will be a superheated vapor because of the elevation in the boiling point. But before that, I need the saturated vapor enthalpy and liquid in here. Can you please do that? I'll just wait. I'll just give you a few minutes, maybe 3 to 5 minutes to do that. Get the saturated vapor enthalpy and liquid at this particular temperature, 137.43. Have it already, class? When you're already taking the quiz, you have to be very fast. I'm using that term very fast because you don't have the luxury of time to waste. So when there's a need for you to go to the steam tables, go right to the steam tables, locate the pressure or temperature that you need as basis, then find the values that you will be needing. Okay, especially if you can do your interpolation directly on your calculators without having to write your columns, your your data in columns, so much the better. Now, if you're going to, for example, if you're solving and you're going to interpolate in more than 5 minutes, my goodness, you cannot finish a double effect evaporation only, especially if there is BPR already. Because it's just not a matter of finding the values from the correct table. At the same time, you have to think as well when you do your energy and material balance. It's not as mechanical as it is. So you have to really manage your time well. Do you have already the HG for this? At a temperature of 137.43 degrees Celsius, you'll be able to read out from your steam tables the saturated vapor and liquid enthalpies. The saturated vapor enthalpy will have to be added with the superheat. What is the superheat? So I will explain it while waiting for your values. The superheat is the product of 1.8 times the BPR of that particular effect in which you are accounting for the H1. In this case, that would be BPR1. So in here, I already placed 1.8 times 3.31 because this is the boiling point rise in effect 1. So the enthalpy that will be or that should be multiplied to your V1 when you do your energy balance for effect 1 later will be this H1, not this one, because that would then be wrong. Now, for your HC2, this will be the spent vapor or the condensate once the energy of the vapor coming from effect 1 was already used in heating the solution in effect number 2. So your HL here will be your HC2 when you do your energy balance. Okay, so Jericho already, thank you Jericho. So you have here for the vapor 2730.51. So you have to place here 2730.51. You need to add these two and this will be the true H1 that will appear in your energy balance. Your HL, which is 578.11, will also be at the same time your HC2 or your H sub C2. Now, you may wonder what is this 1.8? That's your CP. The CP when you're dealing with SI set of units. So CP for the vapor is 1.8. When you're using English units, so I'm making it the same font so you would know, your multiplier is 0.45, not 1.8. So this one is 0.45 for English and you still need to multiply it with the appropriate BPR. You do the same procedure with the other enthalpies in the other effects. So H2 will be Hg2 plus 1.8 times BPR2. H3 will be Hg3 plus 1.8 times BPR3. So those will be the values reflected in the energy balance. Now, another thing that I'd like to discuss with you a few minutes, just a few minutes, is how you are going to report, or where are you going to get the enthalpy of your concentrated liquor, especially, for example, in the case of the enthalpy of liquor 1. So question mark, where will you get the enthalpy of liquor 1? And what will be the basis of getting the enthalpy of liquor 1? It's the same thing with the enthalpy of liquor 2, enthalpy of liquor 3, even the enthalpy of the feed, especially if we're now considering the BPRs. So for this, you will be needing the solids, the X of your particular stream, whatever streams you are accounting for, and their temperature. So you need the X of these streams and their temperature. Now, you may wonder what temperature mix will be used for the concentrated liquors. We don't have any problem with the feed because the feed temperature is taken straight from what is provided in the problem, which is 178.1. As for the concentrated liquor class, the temperature that you will be using is not the saturation temperature, but rather the BP temperature, the BP of your solution. Now, when we were discussing evaporation at the very start, we know that the temperature of our concentrated liquor and the temperature inside our evaporator should be the same. So that temperature is not the saturation temperature, but rather the elevated temperature already. So the BP of your solution will be the one that you're going to use, not the saturation temperature, together with the solid content of your concentrated liquor to get its enthalpy. Question, where will you get the enthalpy of your concentrated liquor? This is where you're going to get it. So I'm going to share again the book. That way it's raw. You get to see it raw. This is for the NaOH water system. You have an equivalent of this in your handbook. It looks similar to this one. But sad to say, it's always NaOH that you have there. So you have here the solid contents on the horizontal axis. So whatever is the solid content, let's say, for example, we are referring to our final product. In our case, the solid content of our final product in the problem that we're working on is 50%. So this is where you're going to start. Then you project up until you reach the boiling point temperature of the first effect, the BP of the solution in the first effect. In our case, I'll just look it up here. The BP of our solution in the first effect is, based on the corrected temperature distribution diagram, is 140.74. I will share it to you so you will see. So the BP that you will use for HL1 will be this BP, the 140.74, together with the 0.5 solid content. So if you go back to that diagram, so you look for 140. If it's not there, you approximate. So you see this one is 121.1. So how many curves you have in between? 1, 2, 3, 4. This is 1, 2, 3, 4. 4 divisions until you reach 148.9. So what I teach my student then is you subtract these two temperatures and divide it by 4 because you have 4 divisions. 1, 2, 3, 4. And then that would be the temperatures of each of the curves here. And you look for your 140. Probably 140 is a little bit below this 148.9 curve. So if you have this 0.5 here, you go up rather until you reach the 148 curve, but you need not reach that because it's 140 only. So it's somewhere here. And since we're working on SI units, then this is where your HL1 should be. So you have 100 up to 600 here. So approximate the corresponding value of your HL1 in here. So that's how you're going to use this particular enthalpy concentration chart for your NaOH water system. Okay? The rest of the steps that you will employ or use will be the same as the steps that I have already outlined to you when we were processing a negligible boiling point rice problem. So we only added the steps that we had in this particular problem because of the BPRs, this one. The first checking that you will do is to check whether the new B1, B2, and B3 is comparable to the first assumed B's, which are equal. If you're okay with that, then you can proceed with the rest of the procedure. If not, then you have to go back. You have to go back to step 4, our step 4, and substitute. You substitute the new B's that you got when you did your material and energy balance, and solve for the new solid content of your effects. If you will solve for the new solid contents of your effects, tanan na siya, ma-chain reaction na. Ma-change ng imo nga enthalpies of the concentrated liquors because it's dependent on that XL, right? So everything will change. So hopefully by that change, you will not have to redo when you are in the part already, when you determine the areas. Okay. If you read further on what you have, what the author there discussed, a second trial is already okay daw. Okay na siyang second trial, you will have a value, a set of values that is acceptable. Okay? Sige. Do you have any question? Have any question as to what we've done today? So from step 7, actually you're going to perform na, I think 6, 7, 8. You're going to start with step 9 na. You do material and energy balances to check the value, the true value of the vapors evaporated in each of the effect, and compare it with what we had assumed originally. Okay, normally class, in this particular part we don't go back. It's okay. It's always based on my experience, it's always in the area where we at times we need to go back to step 4 again because the areas are far from the mean area. Okay, any question?